Good to go.
Okay. Hello, good morning, everyone. My name is Aaryan Dubey, and I'm going to present on evolutionary feature selection, a novel wrapper feature selection algorithm based on evolutionary strategies. So, what is EFS? EFS is a novel feature selection algorithm that selects the best set of features for a machine learning model. It uses meta-heuristic techniques combined with evolutionary algorithm and chaos theory. And also, it uses the concept of evolution, which is the backbone of our algorithm. So, what is feature selection? And it's important. Feature selection is an approach to selecting the best set of features from a feature pool. The goal is to increase the performance of the machine learning model. So, now let's dive into some feature selection steps. So, first step is subset generation. So, in this step, the algorithm tries to generate a subset of features out of a feature set. Let's just say we have a set of features A, B, C, D, E, and F. We generate the subset of features like this: A, B, T, F, A, B, E, F, and A, B. So this is how we generate a subset of features. And after that, we use this subset of features like A, B, D, F in a particular machine learning model and get a score like, okay, 0.85 is the F1 score. So this is how we evaluate the subset. Okay, the subset is performing well. And this process of subset generation and evaluation goes on until a termination criteria is reached. After that, we take the best set of features and evaluate it on our test data set. So this is the feature selection step. Subset evaluation in Python, the step which I told you earlier, we take the subset of feature A, B, E, F, we put it into a function and get an integer value. Here, this is a particular class which uses a function that is found right now. It returns a particular score if we initialize certain features here. Encoding. So what is encoding? It is the process through which we represent our data to a particular format. Famous example for this could be where we convert the decimal number to binary number, like number 6 is converted to value 0, 1, 1, 0. So what is this encoding and how do we use this encoding to encode features? Let's see. First, we need to understand the concept of generation, chromosome, genes, active genes, and non-active genes. First, chromosome. Chromosome is an array where you can store data set right now, like 0, 0, 1, 0, 0. It's our data point that you store in an array. So right now, chromosomes represent that array. Genes represent those data points, that is 0, 0, 1, 0, 0. These data points are known as genes. And inside that data point, the active genes are represented by number 1 and non-active genes are represented by number 0. And if we combine this all data, we put it into a particular set, it is known as a generation in context of EFS. So now let's just see how we encode these features. First, we have a particular set of features. A, B, C, D, E, F, all these features are selected. So we use all the active genes to represent it. A is represented by active gene 1, B, active gene 1. Similarly for C, D, E, F. Now, if we try to encode A, B, D, and F, here A, B is represented by active genes. That is 1 because they are selected. D and F are represented by active gene again because they are selected. Similarly, C and E are represented by non-active genes, that is 0. So this is how we encode our features in the evolutionary feature selection. So what is this EFS architecture that we talk about? First, we need to understand the EFS generation. Generation, in simple words, all the people born and living at about the same time. In EFS, the generation is the number of times the new subset will be generated in the single run of the algorithm. So that means if EFS run for 10 generations, for every run, there will be a subset of features generated encoded in our encoding. So we call this architecture evolutionary strategies. The basic idea for evolutionary strategies is the number of active genes in a chromosome is increased by each generation. So suppose that we have 10 features in our feature set, like feature A, B, C, D, E, F, G, H, I, and J. So in first generation, we can obtain a possible chromosome of value 1 active genes and 9 non-active genes. Similarly, for second generation, we can obtain a chromosome value of 2 active genes and 8 non-active genes. This process grows with the number of generations, as mentioned earlier, so that the earlier generations have fewer genes as compared to the advanced generation. Through this strategy, we can have a set of features that have been truly evaluated over the generation. This particular idea of evolutionary strategies is inspired by the NEAT algorithm, that is the neuroevolution of augmented topologies. Here they evolve the particular neural networks, that is the structure of the neural networks. So we take this idea from there and some concept of evolution to evolve our architecture here. So evolutionary strategies. The basic idea is number of active genes in a chromosome is increased by each generation. So in generation 1, we have chromosome with encoding something like this with only one active gene. In generation 2, we'll have chromosome with 2 active genes. In generation 3, we will have chromosome with 3 active genes. So as you can see, the number of chromosomes are number of active genes in chromosome is increasing by each generation. So what happens in each generation of the EFS? So let's see. First, we create a new random chromosome. We put it into the local list. We evaluate these chromosomes. We terminate some of the chromosomes here that is not useful for us right now. We create the best set of chromosomes. After that, we put the best set of chromosomes into the global list. The global list, it goes to the crossover and the mutation operation. After that, we have a new set of chromosomes generated. New set of chromosome generation will go to the evaluation step again. Again, the termination step will happen. It will again add to the global list. Now, let's understand the random chromosome initialization. So, random chromosome initialization. In general words, this step can be known as the subset generation step. So, in generation 1, we will create a subset of features like this, where we have only one active gene. In generation 2, we'll have subset of feature with 2 active genes. In Python, we represent this particular chromosome with this type of code. So, now let's just see chaotic random chromosomes generation. First, we need to understand some variables. What is pop size? Is the number of chromosomes in a generation, that is 1. Tem size is the number of active genes in a chromosome. Right now, we are using only 4. Number of column, that is the number of feature set, that is right now we are using 10. So, we create a particular loop. We use equation 3 that is written here to calculate init lambda. We take this init lambda, put it into equation 4 in place of lambda list n-1. And we need the value for every active gene that we have. So right now we have 4 active genes. So we'll calculate this value for every active gene. So at the end, we'll have an output of something like this, a particular value for every active gene that we have, that is 4. After that, we are going to use this lambda list value that is here and put it into equation 5. Now we are putting this lambda list value that we have in equation 5 and calculate the value r. We already know what is the value of r, that is 2 into lambda list, n is to number of active gene minus 0.5. We calculated Temp list is the index of our features 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So now for every active gene, we use the R value in equation 5 and calculate our sample. That is an array which will store all the indexes. At the end, the final output will be something like this. 4, 6, 5, 8. That is the number of the active genes indexes. So if we translate it to chromosome, we'll have something like this. 0, 0, 0, 1. That is the 4th index selected here. 5th, 6th, 7th is 0. Now 8th index, 8 is 1. So this is how we generate the chaotic random population for our EFS. So mutation. We use 2 mutation operation. One is simple mutation operation. Here we take a chromosome 1. We select a particular index. In this case, let's just say index that we selected is 2, right? 0, 1, 2. We just flip the bit, that is 0 is converted to 1. So we get our mutated chromosome. So this is known as the simple mutation operation. Now we go to the chaotic mutation operation. We select a particular chromosome, chromosome 1. We take a particular mask and we perform the OR operation between them. That is 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0. So this is how we perform the chaotic mutation operation. After that, we go to the crossover operation. In crossover operation, we use 3 operations. That is the simple crossover operation. Here we take 2 chromosomes, chromosome 1, chromosome 2. We divide those into half. The first half of the chromosome 1 will be inputted here. The second half of the chromosome 2 will be inputted here. And we have our new chromosome. Now, we go to the random crossover operation. Here, we take two chromosomes, chromosome 1, chromosome 2. We select a particular random index. Let's just say index is 4. So 0, 1, 2, 3, 4. We draw a line. We take the first half of the chromosome 1, we put it here. We take the second half of the chromosome 2, we put it here. So by this value, we have a new chromosome value, that is 1, 0, 0, 1, 1. After that, we have a uniform crossover. In uniform crossover, we have two chromosomes, chromosome 1, chromosome 2, and a particular mask that is initiated from chromosome 1. Now, what the mask value will do is, we take the particular value that is 1. So, if the mask value is 1, it will take the value from chromosome 2. If the mask value is 0, it will take the value from chromosome 1. So, this is how we create a new chromosome in uniform crossover. After that, the main thing. Initially, the mask is generated in random chromosome initialization phase. But things differ in case of crossover operation. Let's believe that we have a particular chromosome A and a chromosome B. We perform a crossover operation between them and create a new chromosome, that is chromosome AB. So, what mask will the new child chromosome will contain? And how do we create this mask? Let's see it here. First, we need to use these steps that we have written here. First is convert the mask from gray code to binary code. We already have our mask value from chromosome 1, that is 11001. We convert the mask value from gray code to binary code using step 1. We get the binary mask value, that is 1001. And we initialize the step 2, that is convert the binary mask to decimal using equation 8. We use the equation 8, convert it again. We get the 9, that is the decimal value mask. Now, we are going to use the step 3, that is convert the decimal mask value to real representation using equation 9. We go to the equation 9. We see that K is the number of bits used for binary representation, UL is the upper bound, LL is the lower bound. We use it as 0, we use it as 1. Mask and decimal value we already have, that is 9. LL is the lower bound, we already know it. If you put these values in equation 9, we'll have something like this. 0 plus 9 into 0 minus 1 divided by 2 is to power 4 minus 1. We'll get a real number mass, that is 0.6. After that, we apply the step 4. What is step 4? Step 4 is calculate a new mask value using equation 1. Here, equation 1 is chaotic logistic map equation, where xn is defined by xn, that is the value between 0 and 1. And here, if the theta value is between 3.57 and 4, the logistic map equation is proven to be in a chaotic behavior, excluding some periodic windows. Here, we already know the value of xn, that is 0.6. Theta value is calculated same as we have calculated this value of 0.6. Similarly, as we have written here, similarly for theta mask value 0110, we'll have the value as 1.066. Same as the step we have calculated 0.6. Now, if you put these both values in step 4, now we have the theta value, we have the xn value, and we put in the step 4, that is calculate a new mask value using equation 1. We'll get the value as 0.256. After that, we put the step 5, that is convert the new mask value to decimal value. We get the 3 as the new decimal mask. We use the step 3, that is convert the decimal mask to binary. We convert it, we get 011. We use the step 7, that is convert the mask from binary code to gray code and store it. We have this value 0010, that is the new mask for the chromosome. Some miscellaneous term. What is the local list? Local list is an array which stores the random chromosomes and track them and evaluate them. Evolution step is here we terminate the features that we have created so that it can only pass through the best chromosomes that we have. Global list is the global array which stores all the winning chromosomes through the generation. I'm going to pause here and ask, like, does anyone has any questions right now? No, okay. So after that, we know that these are the things. So simple flow of the diagram, what we have learned right now. We know that what happens in each generation of the EF is, so we run it for 4 generations, right? For every generations, we perform the crossover operation, we perform the mutation operation, we perform the evaluation things. and we update the global list accordingly. And in the whole generation process, global list will have some certain values that will be terminated from it, certain values that will be added through it. The evolution of the creatures will happen in this particular simple flow. And after that, generation 4, we'll just print out the global list and it will have the best set of features. That's it. That's the EFS. We already defined what is chaotic chromosome initialization, how we evaluate creatures, how we select the chromosomes, the global list population, the crossover and mutation operation. That's it. That's the EFS. So, some memory refresher. So, we already know we have chromosome A, chromosome B, the code counterparts of how chromosome A and chromosome B are created. So, let's just say we create a child chromosome, chromosome AB from chromosome A and chromosome B. Right now, you can see we have two parents, parent 1 and parent 2. Parent 1 value is 25, that is, has come from chromosome A, that is the number 25. Chromosome B has the value number 15, it will be used here. So, chromosome AB has been crossovered from parent A and parent B, that is 25 and 15, chromosome A and chromosome B. This will be useful for us to understand this, the evolution cycle of the EFS. So, let's just say, we run the EFS for 4 generations, and the best generation was generation 4, where we got our creature 737 in the 4th generation. The value in the parentheses represent the generation in which the particular creature or chromosome was created. So as you can see, the answer that we have here, that is the 737th creature, was created through the crossover operation, as there are 2 arrows to the particular node from generation 3. And in generation 3 creatures, that is the 597, which was generated in generation 3 through the mutation operation from generation 0. That means generation 0 mutated to form the creature in the generation 3, which in case performed the crossover operation with another creature from generation 3 to create our answer. This is a simple flow of how the evolution cycle in the EFS happens. Let's look at the more complex flow of the diagram. That is this. As you can see, we double the number of generations. Right now, we have 8 generations here. And the generation, that is the 0 generation influence in the last generation has increased a lot. Here we have only 3. Now we have 6. So as you can see, the 8th generation was created from 5th generation and 7th generation crossover. That means 5th generation creature has survived the ordeal of 6th generation, 7th generation, and has come to the 8th generation to form our best creature. That is the 1581th creature that was generated in 8th generation through the crossover operation between the 7th generation and the 5th generation. And also, it doesn't qualify like if you're working like very hard, that you are going to survive through the environment. As you can see, this 4th generation creature didn't make it to the end. That it has any help in creating this generation 8th creature. So it died at the generation 4. So these type of things also happens in the EFS. In the more complex diagram, we will see some creatures value that will be created in generation 4. That means it didn't evolve through any generation. It was randomly created in generation 4 and can help us to reach our best creature. So this is just a simple and some complex cycle of the EFS. So some data set and parameters that we use to test our algorithm. So we use the 10 data sets. Out of the 10 data set, 3 were the multi-class data set and other were the binary data set. The parameters that we used were the number of generations were number of features minus 1. The number of runs that we did were 10. The number of creatures that we created were 200. Experiments. So first experiment that we performed was using the matrix, that is the KNN classifier. The evolution method that we used was the accuracy score. So in table 3, you can see the comparison between the EFS and the other methods that uses the same classifier. That means the KNN classifier. So out of 9 data set, EFS outperformed the other algorithms on 8 data set. And out of 8 data set, we were on par with QBSO-FS. That is in Zoo data set and in Congress data set, we were on par with the QBSO feature selection algorithm. We were outperformed on Sonar data set by CSSA algorithm. After that, we performed another experiment, that is experiment 2. In experiment 2, we used the 3 matrices, that is SVM, naive Bayes, and AdaBoost. We used 2 data sets. In first table, you can see the data set is known as the spam-based data set. And in the second table, we have the data set known as the Sonar data set. The numbers in the parentheses represent the standard deviation of this whole of our runtime in the 10 runs. As you can see in the first table, we were the best performing algorithm in naive Bayes and AWS classifier, but we were outperformed in SVM by PSO algorithm. Other than that, on the Sonar dataset, we were the best performing algorithm out there. As you can see, the standard deviation of our algorithm is lowest in any of the particular algorithm that exists there. So this proves that our algorithm is one of the best feature selection algorithm out there with the most consistent results. So the main question, why does it work? So in the algorithm, the number of generation, that is the number of features, is directly proportional to the number of generations, which gives it a larger search space for a given set of features. This property allows EFS to grow slowly and effectively with the increasing generation, which leads to a better solution approach in most cases. In addition, this property can make the algorithm a time-consuming process for a dataset with a large number of features and samples. So yeah, that's it. And at the end, I just want to thank all the authors, that is Samuel Silva, Pedro Teja, and Alexander Ino, for all the help and support in making this paper successful. Thank you so much, everyone. And yeah, that was me. Thank you so much, everyone. This was presented by me, Aaryan Dubey. You can find the Evolutionary Feature Selection on the GitHub through this link, or just go to the CloudWalk GitHub. It's open source right now. Thank you so much, everyone.
Thanks, Aaryan. Really nice presentation. Really nice that you put GitHub, so it's like open source, CloudWalk open source, right? Initiative. So, guys, does anyone have any questions for Aaryan?
No questions, just another comment. Just so everybody knows, we use this in production here at CloudWalk. So this is what we use to improve our models, and it's really effective, especially for detecting frauds on card loan present. Yeah.
I have a question actually for Aaryan. Like, when did you start working with EFS here? Because I remember it was something that when you entered CloudWalk, you started working, right? So
yeah. The day I entered CloudWalk, I started on this project only, and it evolved through this. This is the final project, final form of the project, I would say. But yeah, still there is evolution thing that we can add on to it. But yeah, the day I entered CloudWalk, I was introduced the neat paper, and then we had this idea, and we worked on it. So,
yeah, you see. And when you entered CloudWalk?
December of 2020. 2020, yeah, December 2020.
Oh, you see? So yeah, really, really good. Really interesting, Aaryan. Congrats.
Thank you so much.
May I have a question for you?
Yeah. Please.
So it's first of all, congrats. That's very cool. And what I think is that it's very interesting. We taking kind of inspiration on how nature works to create a more intelligent exploration of this feature selection space. Do you see any other, for example, you talked about many of the ways that we are combining the genes and mutating them. Do you see any complexity that could still be added to the EFS or to a following model that follows this genetic evolutionary theory, like that was harder to encode, that we were not able to create a different way of visualizing it or to applying it?
Generally, I would say like we depend a lot on, like in CloudWalk problems, I would say we depend a lot on random solution approach. Like any random solution will be created in generation 4, and then we can have an answer in generation 8, something like that. So random chromosome creation plays a very important role. But in other academic, if you go and see the academic papers, they don't depend much on this random initialization. They try to go like from first generation of creatures. So that is something I would love to see, like how a generation creature that was created in generation 1, can evolve to generation 8, something like that. That is one of the things. And other than that, I believe there are tons of things that we can incorporate into this particular algorithm. We still don't know it yet, I would say, but inspiration is all around us, I would say. So every day you see something, and see like, okay, how can we implement it? So yeah, that's the thing.
Okay, I will add something to Joel's question here. Not another question, a comment, like, well, because here we're encoding one feature as one complete gene. And this is not actually what happens in nature. We don't have a pool of genes. Like, you have you have NDA. There's a power bases of per acids. I'm not really sure. Then the combination of these elements, then you create in a sequence. Then you find a gene or create a gene from there is no pool of genes where we active or deactivate. There is only the creation of genes based on raw data. And this is extremely hard to do. Automatic feature creation. So to be able to do this would be a huge milestone. Yeah, and also encoding other stuff, because we are only encoding features here, but the next step is to encode hyperparameters. And this is also hard because hyperparameters are not like discrete, like are active or non-active. They have a value from 0 to 150. How we encode this in a way that is similar to a genetic algorithm, it's not obvious. Also encoding the topology of the model. Like here, Aaryan is using the same architecture for all creatures. Like they're running the same architecture. They're not evolving the shapes of their bodies, what would be the architecture. So there are plenty of stuff to make it more complex, but it's really hard to figure out a good enough way to encode data. Yeah, I would say that.
Very cool. Thanks, guys, and that's very interesting.